Today, we are exploring the kinetic isotope effects. In chemistry, determining the postulation of a plausible mechanism requires the careful analysis of many experiments designed to determine the fate of atoms during the formations of product. Kinetic isotope effect is a powerful tool for this analysis. According to the transition state theory, the reaction rate depends on the energy difference between the reactants and the transition state. So when you substitute a heavier atom to the molecule, the zero point energy will change and it will affect the activation energy, giving the different reaction rate. So that's why a kinetic isotope effect is observed as a decrease in the rate of the chemical reaction when one atom in the reactant is replaced by a heavier isotope. Observing this effect facilitates the identification of bond-breaking events in the rate-determining step. We can categorize the kinetic isotope effects into two types. Primary kinetic isotope effect. This is observed when the rate-determining step requires the scission of a bond involving the isotope, whereby secondary kinetic isotope effect is referring to the reductions in the rate of the reaction even though the bond involving the isotope is not broken to form the product. Then where does this effect comes from? In both primary and secondary cases, the effect arises from a change in the activation energy that accompanies the replacement of an atom by a heavier isotope. This change in this activation energy is the fundamental due to changes in zero-point vibrational energy. Let's look into the basic quantum mechanics of a bond vibration, like a simple harmonic oscillators as shown in this diagram here. So according to the quantum mechanics, the energy level of a bond vibration are quantized, and the energy is given by the equations of En equals to n plus half multiply the reduced Planck constant and the vibrational frequency. N represent the vibrational quantum number. So the n with the value of 0 indicate the lowest energy level for the vibrational motion. Therefore, this is also known as the ground vibrational state. The value of the energy at this ground vibrational energy state is equals to 1/2 multiply the reduced Planck constant multiply the vibrational frequency. So it shows that the molecule possesses a minimum energy, which is called the zero-point energy. The molecule, they are vibrating even though it is occupying the ground vibrational energy level. To solidify your understanding of kinetic isotope effects, let's consider a specific example, the origin of the primary kinetic isotope effect. We are looking at a reaction in which the rate-determining step requires the scission of the CH bond. Recall that a primary kinetic isotope effect is defined by the requirement that the bond involving the isotope must be broken in the rate-determining step. When we perform deuteration, that is, replacing the hydrogen with the heavier deuterium atom, what is the dominant physical change? The dominant effect is that the reduction of the zero-point energy of the bond. The reduction occurs precisely because the deuterium atom is heavier than the hydrogen. We will look into more details later on this one. So now let's consider the transition state, which is also known as the activated complex. In this model, the whole reaction profile is not lowered by the deuterations. This is because the relevant vibration along the reaction coordinate in the activated complex or the transition state has a very low force constant. So there is little zero-point energy associated with the reaction coordinate in either isotopomeric form of the activated complex. This diagram shows the changes in the reaction profile when a CH bond undergoing cleavage is deuterated. To understand this picture, we are modeling the CH and also the CD bonds as a simple harmonic oscillators. Look at the left side of this diagram, which representing the reactant, because the CD bond contains the heavier isotope. Its vibrational zero-point energy is lower than the CH bond. Therefore, the only significant changes in the zero-point energy of the reactants, which is lower for CD than for the CH. Now consider the transition state, which is the peak of the energy barrier. For a primary kinetic isotope effect, we operate under the approximation that the zero-point energy of the transition state is the same for hydrogen and the deuterium reactions, as the bond is assumed to be fully broken or nearly broken. Since the starting point for CH reaction is higher and the transition state is at the same level, the energy gap that must be overcome, which is the activation energy, is different for the two isotopes. So the larger the barrier for the heavier isotope causes the decrease in the reaction rate, which is the definitions of the kinetic isotope effect. By applying the kinetic isotope effects, it allows us to determine which bond in a molecule will be broken down during the product formation. So if we suspect that that particular bond will be broken down, and we need to verify it by substitute the atom which is bonded in the molecule with their isotope. Just for example given here, okay, we have the hydrocarbon chain bonded to the hydrogen bond, and this hydrogen atom, we suspect that it will be broken down during the product formations and give us the R2H. So we need to validate this by replace this hydrogen atom with the deuterium atom. And after we proceed the process of substitution with the isotope, we conduct the experiment and then determine the rate constant. We will find that the rate constant for these two reactions are different, so which gives us a hint that the respective bond which is broken down is the one which is substituted by the isotope, just like the primary kinetic isotope effect that we observe, whereby the rate constant will be different when the molecule is substituted with the isotope. So this gives a very good approximations, because the substitution of the isotope, it changed the zero-point energy of the vibrational energy level. Okay, so we know that for the isotope substituted molecule, they have the same potential energy surface. The shape for this curve are the same. However, because one of the atom is substituted, for example, with the deuterium atom, which is much heavier than the proton, so it will result in the change of the 0-point energy. Now, how to determine the energy for the vibrational level? We apply the simple harmonic oscillators model, where the energy for each of the vibrational quantum level can be determined using these equations here. And in these equations, the omega is represent the angular frequency, where at the ground state, we have the n equals to 0. And at the ground state, the vibrational energy is equals to 1 over 2 multiply the reduced Planck constant multiply the vibrational frequency of the molecule. Now, how to relate this to the energy between the deuterium molecule and also the hydrogen molecule? Then we need to find out what is the respective vibrational frequency for the molecule when it is substituted with the isotope as well as before the substitution with the isotope. We know the 0-point energy is related to the angular frequency of vibrations, and this angular frequency of vibrations can be related to the reduced mass and also the force constant of the molecule. So for the same type of the molecule where they are substituted with the isotope, they have the same force constant. However, the reduced mass for the isotopic substituted molecule, they are different. That is the reason why the 0-point energy for RH and also the R substituted with the deuterium, they will be different because the reduced mass are different. But how to relate the vibrational frequency of the molecule between RD and RH? Before we look into the 0-point energy for RH and also RD, we need to find out what is the ratio of the reduced mass between the two molecules. So we have the reduced mass of RH, Mr multiply mH over Mr plus mH divided by Mr Md over Mr plus Md. Okay, then we will get this ratio for the reduced mass of RH to Rd. And we need to assume that the mass for the hydrocarbon chain is very much larger compared to the molar mass for the hydrogen or the deuterium atom. Then the value of the Mr can be cancelled off in the ratio, whereby the Mr plus mH will be approximate to the mass of the Mr, similar to Mr plus Md. The mass can be approximate to Mr as well, because the mass of Mr is much greater than Md. So we can cancel off the Mr, and it left only the mH over Md. Okay. Therefore, the ratio of the reduced mass for the molecule and isotope substituted with deuterium, it can be approximate to the value of 1 over 2. If we consider the ratio of the frequency of vibrations for RH molecule to the Rd molecule, then what do we get is that we will be able to relate the vibrational frequency for the hydrogen's molecule and to relate it to the vibrational frequency of the deuterium substituted molecule. So the vibrational frequency for the deuterated molecule is much smaller compared to the molecule itself, okay, without the substitution with the isotope, okay, by the ratio of square root 2. Now we can look into some example on the calculations for this 0-point energy between two different types of molecule, where one is a RH, another one is the RD. Please be reminded that the R is referring to the hydrocarbon chain. And assuming that the hydrogen and deuterium atoms are bonded to the carbon. So it is also stated that the IR spectroscopy gives the vibrational wave number for CH is equals to 3000 wave number at 298 Kelvin. Okay, so how to find out the 0-point energy for the two molecules? So how to solve the problem? We need to find out the difference in the 0-point energy between the RH and RD. If we have the potential energy curve, which is oscillate according to the Hooke's law, okay, so it shows the quadratic shape, then the 0-point energy for the RH is at the vibrational quantum number equals to 0, which is the ground state, and at the ground state, the energy value for this level is known as the 0-point energy. So we have two different 0-point energy. One is for the RH and another one is for the RD. Okay, so RD usually has the lower value of energy compared to RH. The reason is that the deuterated atom is much more heavier than the hydrogen atom. So the value of energy is much more lower compared to the RH. So now we have to find out what is the difference between these two levels. Okay, the line of the red and also the green. What is the energy difference, the delta here? So we are also given the value of the vibrational frequency for CH in the units of wave number. Okay, so meaning that this is one of the peak shown in the IR spectrum at the positions of 3000 wave number. We can convert the vibrational wave number into the vibrational frequency by multiplying this number with the speed of light. Okay, so 3000 wave number multiply 2.98 times 10 to the power of 10 centimeter per second. We have to convert the unit for the speed of light from meter per second to centimeter per second. So it is multiply 10 to the power of 10. And the 3000 wave number is equals to 8.94 times 10 to the power of 13 per second. So this is the vibrational frequency for the molecule of CH, or for the molecule which is RH. Okay, so what is the energy difference here? The energy difference can be found by find out the difference between the 0-point energy for the RH molecule and also the RD molecule. So these are the 0-point energy for each of the molecule. The value of this energy can be obtained using the equations here. The 0-point energy equals to 1 over 2 bar H multiply the vibrational frequency, the angular frequency of vibrations. So angular frequency of vibrations equals to 2 pi multiply the vibrational frequency. Okay, so we have to find out the difference between the RH and also the RD molecule. What is the 0-point energy for each of these molecule? So we find out their difference. Okay, we got the vibrational frequency for the RH, which is obtained from here. So we do some mathematics and then we substitute the value of the vibrational frequency for RH. Then we plug in the values of the constant, the Planck constant divided by 2. After that, the vibrational frequency for the RH and also the RD. Okay, the vibrational of the RD can be related to the vibrational frequency of the RH, as we have derived the equations in the previous slide, whereby the vibrational frequency of the RD equals to the vibrational frequency of the RH divided by square root of 2. Okay, so we have this one substituted and we do some calculations where the energy difference between the RH and RD at the vibrational quantum level equals to 0 is about 5 kilojoule per mole. How the difference in 0-point energy we just calculated translates into the difference in activation energy for the two isotopically labeled reactions. We have the reaction profile in this figure where we have the energy for the reactant as well as the energy for the activated complex. Each of them will have their respective potential energy curve and also the value of energy at the ground vibrational energy levels. The epsilon 0 here is referring to the energy difference between the activated complex and also the reactant for the molecule which is bonded to the hydrogen, whereby the epsilon 0, d is referring to the energy difference between the activated complex energy level with the energy at the reactant, which is of this line here. So epsilon 0h is referring to the energy difference between this point and this point, whereby epsilon 0d is referring to the energy difference between this point and this point. So we further determine what is the energy difference between these two transitions. Therefore, we find out the difference between the epsilon 0 and epsilon 0d. If we have this value minus this value, what do we get is that the delta naught, okay, the delta between the 0-point energy. But if we look into more detail, we need to substitute the respective epsilon 0h, which is these expressions, into the equations, as well as these expressions into the equations. Then we will get the activation's energy for the activated complex and also the energy for the reactant. At the positions of this point here where the molecule form the activated complex, if the bond between R and H or the bond between the R with the deuterium is fully broken in the transition state, then the 0-point energy of the transition state for both of these molecules will be the same. Hence, you have these expressions here. Okay, there will have no two lines to separate the energies for the CH and also the C deuterated molecule. There will only remain as the same energy, just one line only. Therefore, if this is true, which means that if the RH will be broken or the RD bond will be broken down, the difference in the energy E naught, which is the same, delta E naught is the same as the difference in the 0 point energy of the reactants. If these two are the same, this one and this one are the same, okay, then they will be cancelled out and left only the energy at the 0 point for RD minus the energy for the reactant of the RH molecule. So which is equivalent or equals to the energy difference for the 0 point potential energy. And we just now in the previous slide, we have already evaluated one of the example whereby the 0 point energy difference between the RD and RH molecule is approximately about the value of 5 kilojoule per mole. From the previous slide, we have seen that the overall change in the activation barrier is determined only by the difference in the energy stored in the stable reactant bonds, not by the difference in the transition state. And now we have to calculate and also relate the 0 point energy difference to the quantitative predictions of the kinetic isotope effect using Arrhenius equation to quantify the rate difference. Recall the standard Arrhenius equation, which links the rate constant to the experimental activation energy and the pre-exponential factor. The kinetic isotope effect is defined as the ratio of the rate constant for the light isotope. So we have the rate constant for the CH molecule to the rate constant for the heavy isotope. Okay, so KCD, which is for the deuterium substituted molecule. We can express this ratio by applying the Arrhenius equation to both of the reactions. So we get the ratio using the Arrhenius equations. And then we have to simplify the mathematics. This expression is transformed to the epsilon 0d minus epsilon 0h. This is something that we derived in the slide before this, and it is equals to the energy at the 0 point level minus the energy for the 0 point for CH, which is the lighter molecule. And if we assume that the ratio of the pre-exponential factor is about 1 for hydrogen or deuterated or the deuterium atom bonded to carbon, then this value here is equals to exponent, the ratio of the rate constant is equals to exponent the delta 0 point energy over RT. And we also found that the delta E naught, this E0 minus E0CH, is equals to 5 kilojoule per mole. Next, we substitute the value of 5 kilojoule per mole into the equations and perform the calculations. We obtain the value of for this ratio is 7.5. So this value of 7.5 is the maximum kinetic isotope effect estimate because it represents the highest rate constant ratio expected if the kinetic isotope effect were determined only by the difference in the 0 point energies of the reactant and if the pre-exponential factor ratio was 1. This value signifies that the reactions with hydrogen atom is predicted to occur a maximum of 7.5 times faster than the reaction with deuterium atom substituted, and provided other conditions are equal. this value, the maximum kinetic effect estimate, it acts as a benchmark against which experimental results are compared. If the experimental results is near to this value here, then it confirms that the bond involving the isotope is almost fully broken in the transition state. So it gives us some hints about which bond is broken down in the formations of the product. We now shift from theory to application. Just now we have calculated the maximum theoretical kinetic isotope effect, where the ratio of the rate for the reactions which involve the cleavage of the bond between CH and CD with the maximum ratio of the rate is about 7.5, meaning that the cleavage of the hydrogen bonding with the carbon atom is about 7 times faster than the cleavage of the bond between the carbon and deuterium atom at 300 Kelvin. So this is due to the difference of the 0-point energy between the CH and also the CD bond in the molecule of the value about 5 kilojoule per mole. In this example here, we evaluate the removal of the hydrogen or the deuterium by a radical from this isopropanol molecule. Okay, so to verify our theoretical predictions, where we say that the CH bond or will be broken, we substitute this H with the deuterium, and then we study the difference between the rate of the reactions. So to verify these predictions, experimentally we measure the rate constant for the reactions between the CH for this molecule and also for the deuterated substituted molecule. We find out their rate constant Kd at different temperature. We also conduct the experiment at different temperature. We use the simple Arrhenius equation, okay, that we discussed earlier to relate the kinetic isotope effect ratio to the energy difference. In order to extract the 0-point energy difference, this value here, experimentally, we plot the natural logarithm. So we have these equations where you have seen in the previous slide. We take the natural logarithm across the equations. After that, we plot the graph of ln kch over kcd versus 1 over t. By having this plot here, it allows us to determine the value of the energy difference, the 0-point energy difference from the slope of this plot. Okay, so we can find the energy difference from this slope here, and for the experiment in this example, they found that the energy difference or the 0-point energy difference for these two molecules is about 4.3 kilojoule per mole. And if we compare this value to the 5 kilojoule per mole which has been determined earlier, it strongly suggests that the CH bond or the CD bond is almost fully broken in the transition state. These two values are very close to each other, and if you still remember, we obtain this value is through the assumptions that the bond between the CH or the CD is fully broken at the transition state, so that the energy level for both of these molecules for the 0 point energy level at the transition state are the same. Therefore, it gives us the value of 5 kilojoule per mole. And in this experiment, the value is determined from the slope, which is 4.3 kilojoule per mole. These two values are very close to each other. So from here, it confirms that the bond breaking event in this experiment here is occur, which involve the bond breaking between the C and also the H. So that is how we apply the kinetic isotope effect to explore the mechanism of a reaction. However, in some cases, the substitutions of the deuterium for hydrogen yield the value of the ratio that is too low, the ratio of the rate constant for the deuterium substituted molecule to the rate constant for the molecule which is with the lighter or the unsubstituted molecule. So this ratio is too low. Even more complete models are used to predict the ratio of the rate constant. This observation constitutes an abnormal kinetic isotope effect, where the reaction for the lighter molecule, which is not substituted with the deuterium one, is very fast compared to the theoretical value. So such abnormal kinetic isotope effect are the physical evidence for the alternative path in which the quantum mechanical tunneling of the hydrogen atoms takes place through the activation barrier. In classical mechanics, a particle can only pass through a potential energy barrier if it possesses enough kinetic energy to get over the barrier. However, a quantum particle can sometimes sneak through a barrier even when its energy would seem to trap it on one side. This ability to bypass the potential energy barrier is known as quantum mechanical tunneling. Classically, when the potential energy equals the total energy, the kinetic energy and the velocity are zero, and the oscillator cannot pass this point. A quantum mechanical oscillator, however, has a finite probability of passing through this point. For molecular vibration, this property means that the amplitude of the vibration is larger than what it would be in the classical picture. In some situations, a molecule with a larger amplitude vibration could enhance the chemical reactivity of a molecule. So in classical mechanics, a particle can only pass through the barrier if it has enough kinetic energy to get through the barrier in the potential energy. A quantum particle can sometimes sneak through the barrier. Instead of going through this path, it will just sneak through here when its energy would seem to trap it on the other side. So this effect is called a quantum tunneling, and it explains how trapped nuclear particles can sometimes escape their nuclide, leading to the radioactive decay. Tunneling also allows photons of visible light to escape the interior of the Sun and electrical currents to function. So some of the abnormal kinetic isotope effect, the values will deviate from the classical prediction value, where when you compare the deuterium substituted with the non-substituted, usually the value of the rate constant is about 7.5, and if they have the deviations, then it is necessary to explain the variations by the quantum mechanical tunneling. From the quantum mechanical perspective, there is a finite probability of wave functions or a particle appearing on the other side of a finite potential energy barrier. Remember, the critical consequence for a reaction is that there is a chance the reaction can proceed from reactant to the product without going through the potential energy barrier. And this phenomenon is known as the tunneling effect, where the particle they just sneak through the barrier. While the tunneling effect is heavily dependent on the mass of the molecule, the light elements such as hydrogen as compared to the deuterium atom will tunnel more efficiently. This means the light isotope's rate constant is preferentially accelerated by the tunneling effect compared to the rate constant for the deuterium molecule. This preferentially increase the rate constant and for the hydrogen molecule and leads to an increase in the kinetic isotope effect at low temperature as well. So we will observe that for the plotting of the Arrhenius equation, where we have the ln k plotted against the 1 over t, normally the Arrhenius plot should be a straight line. However, the presence of the tunneling will result in an upward curve in the Arrhenius plot at low temperature, where at this region here, if the reaction temperature is low. So the presence of the tunneling results in an upward curve in the Arrhenius plot, and these deviations from the linearity provides a spectroscopic proof that the hydrogen atom is bypassing the full activation barrier while quantum tunneling occur and increase the observed kinetic isotope effect beyond the maximum classical value predicted, which is just only based on the energy, 0-point energy difference. We have used concept of transition state theory embodied by the Eyring equation to move beyond simple Arrhenius kinetics. So the transition state theory offers a few advantages for the understanding of chemical kinetics. It builds in collision theory, but it goes further by allowing the molecular complexity. Transition state theory provides a good estimate of the pre-exponential factor in some cases. Recall that the empirical Arrhenius equation will treat the pre-exponential factor simply as a constant, but transition state theory link this pre-exponential factor to the fundamental statistical mechanical properties such as the partition function. So most importantly, for the current discussion, transition state theory also provides a qualitative explanation of various phenomena, which include the temperature dependent of the rate constant, the kinetic isotope effect. Although the simple energy difference, which is referring to the 0-point energy difference, it gives us the maximum value of the transition state theory, or the maximum value of the kinetic isotope effect. It provides a theoretical framework for calculating this ratio of the rate for the reactions. Anyhow, the transition state theory is limited by the ability to probe the transition state. The transition state itself is a fleeting configurations of atoms, and it is difficult to verify the theoretical assumptions about its structure. Other than that, computational difficulties is also another issue, whereby calculating the necessary partition function for reactant and activated complex becomes highly complex as the molecular size increases. So in summary, the transition state theory provides a good theoretical foundation for the understanding rate constants and effects like kinetic isotope effect to predict the mechanism, but its complexity and reliance on defining an unobservable transition state limits its universal applicability.